It's obvious that U values are going to be really impactful on our passive house. The level of insulation is going to be one of the key drivers of the overall building's performance level in a cold climate like New York. So we know that they're going to be really critical. We also know that the PHPP is not going to be able to do its work without these U values. So the U values are going to be absolutely central to the primary function of the PHPP to calculating heat transfer through all of the various surfaces. But what we would like to do now is take a few minutes and talk about where the heck did these numbers come from. So they're super important, but where do we get them from? So how do we determine the U values for our project? Well, U values in practice are going to come from essentially one of four different places. So one of four different locations. They're either going to come from your local, state, federal, local building codes, one of your whatever your code reference documents are that govern your building and your location. They might have some U values that you might use. We'll look at some examples of that. You might get U values from some sort of engineering reference document. So there's a couple of different examples that we might look at. You might use numerical calculation methods like the PHPP. We'll look at the PHPP's built-in numerical assessment methods for calculating U values. Or you might use something like a 2 or 3-dimensional heat transfer simulation, something like Therm or Flixo or Scytherm, Passitherm, Mole, Dartwin. Any of those different programs would be able to calculate a U value as well. So actually quite a few different places, quite a few different methods that we can use to determine U values for our assemblies. So U values are very important, and it's important for us to calculate them accurately. But the part of the complexity here is that we can actually get our U values from any of several different sources. And depending on who we're doing the modeling for, we actually might want to choose one source or another. So first of all, let's just start by talking about building codes. So I'm sure anyone who's an architect or builder, an engineer who has worked on a project that required some sort of code compliance is familiar with local building codes, which are in many cases going to include things like this table right here. What is this? This is just a table drawn from a local building code here in New York that has a table that shows you effective R value for certain thicknesses and stud spacings for steel stud elements. So let's say that you wanted to include an assembly like this in your building energy model. Well, one place that you could go to get a effective R value or U value, as we know we can convert back and forth between R and U values, one place you could go to get the number, the right value to use, would be a table like this. And there are lots of these types of tables built into building codes. So in certain circumstances, this would be the appropriate place to go and get a number and then use that in the PHPP. And we'll see how we can deploy that in a little bit. So this would be one source. We could look to our local building codes. We could also look to some sort of an engineering reference document, in particular the documents that I'm thinking of and the documents that we would use for this purpose would be something like ASHRAE 90.1 Appendix A. Appendix A is the appendix of 90.1, which includes all of the rules around calculating U values or R values, as well as a whole set of tables that can give us things like U values for different stud spacings and different insulation depths and different assembly types. There's a whole universe of different assembly types and giant tables that exist in Appendix A, and we can just go and find our assembly type and pull it from the table there and deploy it into our project. Now, in particular, if you are doing some sort of a commercial project which requires an energy model to be made following ASHRAE 90.1, then you probably do have to use the values that you find in these tables. Although we will see that there are some exceptions there. Sometimes we are allowed to go calculate our own. But keep that in mind. If you're doing some sort of commercial compliance, obviously you wouldn't be using PHPP anyway, but certainly you would have to follow the 90.1 Appendix A rules and guidelines and conventions. Now, 90.1 is not the only reference document that we might look to. The BC Hydro Thermal Bridging Guide, on an outgrowth of the ASHRAE Research Project 1365 around thermal bridging and heat transfer in assemblies, is a fantastic reference guide, reference manual. It is an enormous, very thorough compendium of not only a huge variety of construction assembly types, but also thermal bridging values for typical junctions and connections and certain architectural and construction details. It started out life as a giant 400-page PDF that was freely available through BC Hydro being a utility up in British Columbia, who partly funded and distributed the guide there. Was mostly developed, as I understand it, by Morrison Hirschfeld. Again, this was part of the ASHRAE Research Project 1365, which is pretty old at this point, maybe 10 years old now, I think. In any event, this is a great guide, a great place to go if you're looking for U values or R values for lots of different assemblies. It definitely has a, let's call it a commercial construction sort of bent, meaning that most of the content that you'll find in this particular reference document is going to be of sort of commercial character, a lot of steel stud, a lot of high-rise facade elements, that kind of thing, but very useful in many ways, and a great guideline for getting U values as well. In particular, what you'll find in the online component, so as I said, it started out life as a giant PDF, but nowadays it's a website, an interactive website where you can sort of select different assemblies and increase and decrease their thicknesses, etc. And what you'll find are things like, okay, well, if you've got 4 inches of exterior insulation and you've got this type of facade clip, well, here's the expected U value. And if you have 10 inches of insulation, well, here's the expected U value. And so they have a lot of elements like the one shown here. This is also from that BC Hydro guide, where you can sort of figure out your assembly and where your assembly lies on this curve, and have a U value associated with it. So this would be another good source for U values if you're looking for U values to use in your project. Now, those guides are all great. The fact of the matter is that for passive houses in particular, most of the assemblies that we're trying to build are not actually in those guides. Right? Those guides and reference documents are mostly for code compliant construction, and most of the kind of stuff that we're doing is going to be, a lot more insulation, a lot different than typical code construction assemblies. Well, okay, so what does that mean then for passive housers? Well, what it sort of means is that we are left calculating our U values mostly on our own. So we have to go calculate our own U values for our own assemblies for the most part. Now, this is allowed. There are procedures for this. In ASHRAE Appendix 1, they outline, if you're calculating a roof, use this calculation method. If you're calculating a wall, you can use this calculation method. If you're doing a floor, you can use this calculation method, etc. So it is an approved methodology in ASHRAE land, and it is a all but required methodology in Passive House land. One of the complications of doing Passive House in North America, of course, is that we have these dueling sort of governing bodies. We have both the PHI and the international reference standards, and we have the ASHRAE reference standards, and we have to kind of keep one eye on both of them and make sure that we're sort of satisfying both. They're mostly in alignment, although not always, and so that does make it sometimes challenging, especially as we get to larger, more complex projects. Okay, so in Passive House world, we're going to go off and calculate our own U values for the most part. So how are we going to do that? Well, let's look at the calculation methodologies that we would use to calculate our own U values. And let's look at the different processes as they are outlined. So first of all, in ASHRAE Handbook of Fundamentals, Chapter 25, really Chapter 27 more than anything else, Chapter 27 is going to outline the different methods, the different ASHRAE methods for calculating U values of whole assemblies. In fact, Chapter 27 outlines not one, but 3 different methodologies for calculating U values of assemblies. the so-called parallel path method, the isothermal plane method, and then a whole different weird method called the zone method. We're not going to talk about that one at all. We don't really get into that one. But there's essentially 3 different methodologies for calculating heat transfer through assemblies outlined in Chapter 27 of your ASHRAE Handbook of Fundamentals. Now contrast that, or sort of alongside that, we have the ISO 6946. So we have, again, 2 different engineering reference guideline documents. We have ASHRAE Handbook of Fundamentals, Chapter 27, and we have ISO 6946. And they are mostly the same, although there are some small differences, very, very small, very, very minor, but there are some very small differences between them. So just keep that in mind. We have these 2 different guideline documents that we kind of have to keep, as I said, keep one eye on both of them as we do this type of work here in North America. So ISO 6946 is the ISO document that the Passive House Institute is going to reference, that they're going to point to in all of their guideline documents. They don't really know anything about ASHRAE. Obviously, they're headquartered in Germany. They don't really know anything about the United States. And so they don't ever reference or point to ASHRAE documents, although, of course, our building codes do. And so we, in most cases, practically speaking, have to demonstrate compliance with both ASHRAE and ISO requirements and rules. So in any event, how are these guidelines going to tell us to calculate the U values of our construction assemblies? Well, let's take a really simple one. Let's take an easy one. Let's look at something like a SIP panel. So a SIP panel, a structural insulated panel, this is from ASHRAE Handbook of Fundamentals, Chapter 27. This is the example that they use. That's a pretty straightforward example because it's just a continuous or homogeneous layers of material. So we've got a continuous layer of gypsum, a continuous layer of expanded polystyrene, a continuous layer of sheathing, etc. So given that we've got a very simple assembly, like a SIP panel assembly, how do we calculate the total U value of that assembly? Well, we actually don't calculate the U value. What we actually calculate is the R value. And we're going to calculate the R value by calculating the resistance of every layer and then simply summing up all of those individual resistances. So I'll say that again. We're going to calculate the resistance of every single individual layer based on its thickness and its resistivity. And then we're going to sum up all of those resistances to give us a total resistance for the whole assembly. And then, as we've talked about, we can flip over to U value by simply taking the inverse of the R value being the resistance of the assembly. So for instance, we might take the vinyl siding. It's R value of 1.24 per inch. It's a ½ inch thick, and so that gives us a total resistance for the vinyl siding layer of 0.62. You see the building paper gives us an R per inch of about 1, but it's only very thin. It's only about a 1/16 of an inch. So that gives us a total resistance for that layer of 0.06. The OSB is an R per inch of 1.24. It's a ½ inch thick, so that gives us another R of 0.62. Then the XPS foam layer, the expanded polystyrene layer, that's got an R per inch of 5, so a much higher R per inch, and it's a lot thicker, so it's 6 inches. So you can see there, that gives us a total layer resistance of 30. And then lastly, we have our gypsum board, an R per inch of 0.9, total thickness of ½ inch. That gives us a layer resistance of 0.45. If we sum all of those up and we add to them the RSI and the RSE, the surface film resistance on the interior and the surface film resistance on the exterior, that gives us a total assembly resistance of 32.6. And we can get the U value of that by simply taking the inverse, by taking 1 over 32.6, and that gives us a total U value of 0.031 BTUs per hour, square foot degree Fahrenheit. Again, if you want to see more extended discussion of this calculation, you can check out your ASHRAE Handbook of Fundamentals, Chapter 27. This is the first example in that chapter. Pretty straightforward, though, right? I mean, there's a lot of it. There's a lot of data to keep track of, but the mathematics are quite straightforward. We take the R per inch, we multiply it by the thickness to get the total layer resistance. Then we just add up all of the layer resistances. So pretty straightforward. However, That method works great when we have homogeneous assemblies, where we have just a consistent, constant layer of material for the entire assembly. Unfortunately for us, most of our assemblies are not built that way. Most of our assemblies are actually made of a mixture of different materials. For instance, a stud wall, where we've got some studs spaced out, spaced apart from one another, and then we've got some insulation in between the studs. This assembly here is a typical tripartite assembly that we might have on a passive house building, where we've got our typical stud wall, we get some continuous exterior insulation on the bottom, and then we have a service cavity on the interior, and maybe we would insulate the service cavity as well. So we've got these 3 layers of insulation, and some of them are made of a mixture of timber and insulation. So how do we deal with that situation? After all, in this situation, some of the heat flow is going to go through the insulated portion, and some of the heat flow is going to go through the timber portion. How do we sort of dole that out? How do we calculate that? Well, ASHRAE tells us that, in fact, we can calculate that in 2 distinct ways. So the first way, well, 3 really, but we're only going to look at 2. So of the first way that ASHRAE says we can, and ISO 6946 say that we can do this math, is by using the parallel path method. And the way the parallel path method works is that we're going to calculate the total resistance for each of the heat flow pathways in the assembly. We're going to calculate a weighted U value for each of those pathways, and then we're going to combine those weighted U values. So for instance, I'm going to calculate the total resistance for pathway 1. What's pathway 1? What does that term mean? Well, if you look at the diagram on the right-hand side, pathway 1 is the characteristic heat transfer pathway represented by gypsum sheathing, insulation, insulation, timber, insulation, and then out. So if we were to calculate a total resistance of that pathway, we could do it as shown in the table there on the left. So we might get a total R value, a total resistance for that pathway of something like 45.2. How do we calculate that? Well, we do it just the way we just saw. We take the R per inch of each layer, we multiply it by the thickness of that layer, that gives us the total resistance for the layer, and we just sum up all of the resistances of all of those layers. So we get an R45. That's pretty good. Well, except that sometimes, every once in a while, we have these wood studs that get in the way. So now we have a second characteristic heat flow pathway. And if we were to calculate the resistance of that second pathway, pathway number 2, so you can see that we would come up with an R value, a total resistance value for that pathway of only 33 or 33.7. So 2 distinct pathways with 2 very different resistances. So how do we combine those together? Well, the way that we combine those together is that first, we convert those resistances into U values. We convert those R values into U values by just taking the inverse. Then we're going to multiply those individual pathway U values by an area weighting factor. So that area percentage describes how much of the total surface area is composed of each pathway. So in this case, pathway 1 makes up 90.6% of the assembly. Pathway 2 makes up 9.4% of the total pathway. How did you get those numbers? How do we calculate those numbers? Well, there's nothing very magic about it. You just calculate the spacing of the studs and the width of the studs, and you figure out how much of the total assembly surface is made of pathway 2 and how much is made of pathway 1. You could draw an elevation of the building and sort of count the surface areas, or you can do it mathematically. Somehow you just want to figure out how much is made of pathway 2 and how much is made of pathway 1. And you can see when we do that, what we end up with is a weighted U value. So the weighted U value for pathway 1 is 0.02, and the weighted U value of pathway 2 is 0.0028. And so what do those mean to one another? Well, we're just going to add them together. Those both represent a certain amount of heat transfer. We just add them together to get a total U value of the assembly of 0.0228 BTUs per hour square foot degree Fahrenheit. And of course, we can convert that into an R value very simply by taking the inverse 1 over 0.0228. So that's one method. We can use that method to calculate an R value and a U value for an assembly like this, absolutely. Now, there's another method, however, outlined in the ASHRAE Handbook of Fundamentals, Chapter 27, and ISO 6946, and that's known as the isothermal plane method. And the isothermal plane method is going to work a little differently. The best way to imagine it is imagine if you took that heterogeneous layer, you took all the timber and you took all the cellulose and you combined them together into the world's most disgusting milkshake, and then you poured that sort of uniform mixture of wood, fiber, and insulation into that layer as like a cake mold or something. And then we calculate the total resistance of the entire assembly using that new hybrid material with equal parts or appropriate parts, timber and insulation. Mathematically, how would we do that? Well, we would do it in a very similar fashion to everything we've seen so far. So we're going to try and calculate the total resistances of every layer. The complexity in this case is that we want to calculate a mixed or hybrid resistance for that mixed or hybrid layer. So notice it's very similar to the math that we did in the parallel path method. We're going to calculate a U value. We're going to apply an area weighting percentage. We're going to calculate a weighted U value. The distinction here is that we're going to do it just for the heterogeneous or mixed layer, isolate it all on its own. We're going to come up with a total resistance for that layer all on its own, and then fold it back in to the total assembly at the very end. So in this case, we add up all of our items at the end there, and we get an R value of 42.5 or a U value of 0.0235. So two different methods of calculating heat flow for those heterogeneous assemblies. Well, that's interesting. So the parallel path method gives us a U value of 0.0228, and the isothermal plane method gives us a U value of 0.0235. Well, those are not the same number. So which one of those is the right number? Neither. The parallel plane method is going to give us a slightly low figure. The isothermal plane method is going to give us a slightly high figure. So the way that we do this in practice is we average the two values. We're going to put those two values together, and we're going to come up with an average value, in this case 0.0232. And that is exactly what the PHPP is going to do. Now, luckily for us, when we turn our attention to the PHPP, we're not going to have to do any of that math. All of that math, the structure of that, or both of those algorithms, is baked into the PHPP. What we're going to do is we're going to describe our assemblies to the PHPP within one or another of these numerical constructors. So PHPP includes a whole universe of these numerical constructors to allow us to build our catalog of our own assembly types. And what we need to do is we need to describe to PHPP all of the various thicknesses and resistivities and surface film conditions, area weighting factors, etc., for all of the different bits and pieces. And then PHPP is going to take all that, it's going to go off and calculate all of that stuff and put all that stuff together for us. But the way it's going to do it in the background is going to be exactly the method that we just saw. It's going to do it using the parallel path method and the isothermal plane method, and it's going to average the results between the two in order to yield to us a total R value for quite complex assemblies. We can model reasonably complex assemblies within these numerical calculators or numerical constructors. So we will see, and we will execute several of these for our example building moving forward into the next section. So we'll see this in quite a bit of depth moving forward. But this is what's happening in the background. This is what the PHPP is doing. Now, all that said, there are other methods, and in particular, there are certain assembly types which are going to require us to use alternate methods. So the numerical constructor method, the parallel path method, and the isothermal plane method are not going to be the appropriate solution for every type of assembly. Some assemblies, very complex assemblies, and assemblies in particular that use things like steel studs or steel floor or floor joists or steel rafter joists or rafters, those types of assemblies cannot, may not, and cannot be modeled using a numerical method. In those cases, or with really complex assemblies, we're going to have to shift gears and go off to something like a two-dimensional or three-dimensional heat transfer simulation program, like Therm or Flixo or Passitherm or Heat 2 or Heat 3 or Dartwin or whatever your simulation tool of choice is. It's very common to have to shift gears and go off and calculate those things explicitly in a program like that, and then import or take that data back into the PHPP. And we'll sort of look at a couple different methods for how one might do that. So we'll sort of play that out for sure. So that is just a brief survey of U values. Obviously, there's a lot more detail that we could jump into on any one of those topics, but hopefully that gives you at least a little bit of a 30,000-foot view of U values. When we come back in the next series of videos, we'll turn our attention back to the PHPP itself. I think we finally have enough grounding and enough understanding of U values that we can now start to look at how we're going to actually build some actual U values in and for our actual project. So when we come back, we will, as I said, turn our attention back to the PHPP, and we'll look at how we're going to actually use those numerical constructors to make ourselves some U values.